You have 7 chips. Your opponent has the rest of the table, all the way up to 20. You flip a fair coin. Heads, 1 chip moves to you. Tails, 1 moves to them. Nothing here is rigged. There is no house edge, no hidden fee, no commission, and no bias in the coin at all. On screen, we will track your pile as a single counter, because that is all this game really is, one number that moves up or down. The game ends in exactly 2 ways. If your pile ever reaches 0, you are out, and you cannot come back. If it climbs all the way to 20, you have taken the table, and it is over. That is the entire game, and you now know every rule of it. So here is the question. Why does a fair game still ruin the player with less money? And it matters far beyond a card table, because this is the shape of any system that can run out of something it has no way to get back. Before the simulation runs, commit to an answer, because your instinct is the thing being tested here. With a genuinely fair coin, do you have a fair chance of reaching 20 before you hit 0? Most people say yes, or something close to yes, and the reasoning feels solid. The coin is fair. Each step is fair. So the game should be roughly fair. Hold on to whatever you just decided, because the answer is not close to it. Look carefully at the 2 ends, because they are not the same kind of boundary at all. The floor at 0 is absorbing. Once the counter touches it, the game is over permanently, and there is no rule anywhere in this system that lets it climb back out. It is not a setback. It is an ending. The ceiling at 20 also ends the game, but it is a target rather than a trap, and the counter has to travel much further to reach it. Now notice where the counter starts. It begins much closer to the floor than to the ceiling. That asymmetry is the whole story, and it has nothing whatsoever to do with the coin. The coin stays perfectly fair for every single step it takes. It also has no memory. A run of bad luck does not make good luck more likely afterwards, because the coin does not know what it did before. What is unfair here is not the odds. It is the distance to each exit. The counter needs only 7 bad steps to be finished forever, and 13 good ones to win. Those 2 numbers are the whole game, and neither of them is the coin. Watch a single run. The counter drifts up, then down, then up again. This is a random walk, and across any short window, it genuinely does look like it could go either way. Notice how often it recovers from a bad stretch. That recovery is completely real, and it is exactly what makes the game feel winnable while you are still inside it. This is worth being honest about because it is not an illusion. The counter really does climb back. Some runs climb back several times. That is precisely why the trap works. Every recovery is evidence, and the evidence points the wrong way. Now watch what happens the moment it touches the absorbing floor. Nothing recovers. The run simply ends, mid-story, with no resolution. Play the same setup again, and the path is different every time, but the shape of the risk never changes. Across the runs we are about to do, a game lasts 90.6 steps on average before it finishes one way or the other. That is easily long enough to feel like a fair fight while it is happening, and long enough to build a whole theory about how you're doing. Now stop trusting a single run and do 8,000 of them. Same fair coin, same start at 7, same absorbing floor at 0, same ceiling at 20. Every finished run gets recorded as either a win at the top or a ruin at the bottom. Watch the 2 piles grow. They do not grow at the same rate, and the gap between them opens early and never closes. Notice also how varied the runs are. Some finish in a handful of steps. Others wander for hundreds before resolving. If you only ever saw a few of them, you could come away with almost any impression you liked, which is exactly the problem with judging this from experience. When all 8,000 runs are complete, the counter reached the ceiling in 0.3548 of them. That is nowhere near half. The theory predicts 0.35 exactly, and the simulation lands within a whisker of it, which tells us the simulation is not doing anything strange. And not one single run timed out, so there is nothing hidden in an unfinished game. So answer the question directly now. In a fair game, what decides who is most likely to be ruined? Take a moment before the answer appears on screen. Here it is. The ratio of the two bankrolls decides it, not the odds of each bet. The counter started at 7 on a scale that ends at 20, and it reached the top in very nearly that same fraction of runs. Your probability of surviving is simply your share of the total money on the table. That is the entire result, and it is worth reading twice. The coin never mattered here. That is not to say odds never matter. Tilt the coin even slightly, and this result changes shape completely. But hold the coin fair, and the only thing left deciding who walks away is where each side started. Now the honest limits, because this is easy to overclaim. This is a simplified walk with equal steps and one absorbing floor, not a model of any real casino game. Real games add a house edge on top of everything you have just seen, which makes the picture worse, not better. And the claim is not that winning is impossible. Plenty of individual runs did reach the ceiling, and you watch them do it. The claim is narrower and far more useful. With a fair game and unequal bankrolls, the smaller stack is ruined more often, and that effect comes entirely from the fact that 0 is absorbing while the opponent's limit effectively is not. It is also worth killing one common escape route. Betting larger amounts to recover faster does not fix this. It shortens the walk, which means fewer steps and less time for luck to average out, and it brings the absorbing floor closer. You do not change the shape of the problem by playing it faster. So a fair bet repeated forever is not a fair outcome. That is the takeaway, and it survives well outside gambling. So take it somewhere new. Where else does a system fail because one side cannot recover from 0? Think about a small business running out of cash while a competitor can absorb a bad quarter, a population dropping to its last breeding pair, or a spacecraft with a fuel budget and no way to refuel. In every one of those, the losing state is permanent and the winning state is not. Same shape, same absorbing floor, completely different field. Once you start looking for that asymmetry, you find it everywhere, and it explains why being well capitalized is often worth more than being right. The next episode stays with counterintuitive probability and asks how few people need to be in a room before two of them almost certainly share a birthday. The answer there is just as far from intuition as this one was.